you like me to time you, Chris?
No, it's all right. Cool. Can you see my presentation?
Yes.
Brilliant. Okay. So yeah, this is a practice for a talk that I need to record for the BNS conference. It's quite weird looking at a picture of us on a Zoom call while on a different Zoom call at the moment. But yeah, so I thought this would be a good idea to give myself a kick up the bum to get the talk written, and predictably I've done this at a bit of a rush, so it won't be extremely polished, but anyway, I will record myself. Okay, so in my group at Sussex, we're interested in looking at how we remember events from our lives. So this shows what in the olden days we called a foreign holiday, where we could go abroad. And so you've got some pictures, it's a bit old now, of me and my family in Venice. And you see some different things that happened to us during the day. Now I'm going to show you a sort of summary of the kind of ideas people have about how such events are kind of processed and remembered. So the idea is that when we're in an event, when we form a representation in our minds of what's currently going on. And this is our sort of online representation of the now. And the idea is that this is stored in working memory. And by working memory, I don't mean a kind of phonological leap that you'd store digits in, but it's more the things that we're currently consciously aware of. And there's good evidence that we represent this information in what's highlighted in the blue here, in cortical regions that correspond to the brain's so-called default mode network, but also are characterized as being long timescale brain regions. So they seem to assimilate and integrate information over the order of tens of seconds or even minutes to kind of update our representation of what's currently going on. So this seems to be all represented in the cortex, and it's our kind of representation of the current situation. And then as we transition between different events, so we move from waiting to go on a gondola ride to actually being on that gondola ride, we transition between different events. And at those transitions, at those event boundaries, it's thought that the hippocampus encodes the information about what's just happened into long-term memory, so we're able to remember it later. So this breaks down really into terms of working memory supporting what's currently going on right now. And every time you have a transition between events, you encode information into long-term memory. Now, amnesia is an impairment of long-term memory. So generally we think that our working memory is intact, or in an amnesic, your working memory is intact, whereas long-term memory is catastrophically impaired. And so it seems that this model should have some predictions about things that you would see in people with amnesia if they are performing a kind of event processing task in the scanner. But so far, these models have only been based on data from healthy adults, and we haven't looked at patients. So these are some questions that I think we might want to try and answer if we were scanning people with amnesia. So the first thing is whether processing of ongoing events, of the events currently we're engaged in, is normal in these long timescale cortical regions. We also might want to see whether hippocampal responses that are related to memory encoding are abnormal or changed. We might be interested in whether the interactions between these long timescale cortical regions and the hippocampus are normal. And we also might want to look at what's happening when we're actually retrieving and remembering these events. Are things there abnormal? So just recently, there's been 3 different studies that have aimed to look at this, and they're very much sort of first pass studies to try and tackle some of these questions. I'm not saying that these studies were specifically trying to address these particular questions, but they're the questions that I think are most interesting. So the studies are this one from Marie St. Laurent, and this came out last year in Neuropsychology. This one, I cannot pronounce this person's first name, but if anyone on the call can, then please tell me afterwards. Their surname is Zhu. And then a study from our lab that was carried out by two former postdocs, Chrissy Oderkoven and James Kydell, that we published in 2019. So what I want to do is summarize the results of these three studies and see how far we've got towards answering some of those questions that I highlighted. So just to give you some details about the patients. So in our study, we were testing a 75-year-old man who had a sudden onset amnesia that seemed to correspond to him having a right thalamic stroke, which is highlighted here. But also on MRI, we could see that his left hippocampus was markedly shrunk. And in the next study by Zhu et al., they were testing a 63-year-old man who had very extensive bilateral medial temporal lobe lesions caused by encephalitis, particularly on the right. You can see these areas damaged over here, but on the left as well, affecting a lot of the medial temporal lobe and some other areas too. And then the last study by St. Laurent et al. Tested a developmental amnesic. So this was someone who was 20 years old, who'd had a stroke aged just 10 days old, which caused, you can see, area in the right thalamus, but was also apparently in the left as well. And this individual has then grown up, not being able to doesn't have a functioning episodic memory. So those are the patients. I'm now going to summarize the tasks. So to give you a sort of overview, they all involved getting people to watch or listen to sort of narrative videos or stories while in the scanner, and then try and remember them afterwards. And none of the patients were able to remember at all accurately the information that they saw within the scanner. In our study, what we did was we showed people videos that were about 40 seconds long. They showed meaningful interactions between people. There was a sort of short narrative storyline to them. They each had a title to them, like Nasty Neighbours, and they'd watch one, and then after a brief pause, they'd then try and remember that. They were given the cue. The screenshot of the start of the video disappeared, but the title remained on screen with the instructions to remember it for up to 55 seconds. And they went through the test like this, and then afterwards we tested their memory. In the study by Zhu et al., they listened just to one story, which was a sort of amusing monologue, initially performed live as a kind of short story. So they were just listening to the audio of this story, lasted about 7 minutes. And they also listened to a scrambled version. So they took paragraphs of the story, but then jumbled up so that it didn't make sense. And I'll explain why they did that later on. And then in the St. Laurent task, this kind of didn't use narrative so much. So this used very short 3.6 second audio visuals where you would see a short video clip of something like an avalanche, and you'd hear the noise of it as well. So these were very sort of rich stimuli, but they didn't have any kind of narrative storyline to them. And they just watched and then recalled these clips in the scanner. So to summarize this, so in the Oderkoven Kydell et al. Study, people were watching just 8 films that were about 40 seconds long, had to watch and recall them. And we just looked at the overall level of activity while people were watching and recalling these videos, as well as functional connectivity. And then in the Zhu et al. Study, they were listening to this audio narrative, and in their analysis, they focused on pattern similarity. So this is a good way of looking at narrative video data. If you've got quite long chunks of the story or the film, and you can look at the degree of similarity across participants. And the idea is if you're watching the same thing as something else, and activity in your brain is doing the same kind of thing in your brain as in someone else's brain, then that activity must be related to your processing of that video in some way. And so your pattern of brain activity looks similar to someone else's when you're watching the same thing. And I'll talk about where you see that in the brain. And then for the final study, using these very, very short clips, there were just 11 clips, but they were repeated in 7 runs. So this gives you a lot of data to do a multivariate classification. So you could look at the activity while people are watching or recalling the same clips, and you can try and classify on the basis of that activity which of the different clips it must be. So it's related to the specific clips that people are watching or recalling. It's not just sort of the activity in the brain while you're watching or recalling something, but it's actually representing the information in those clips. And so with those different analyses, you can answer different questions. Okay, so in our study, when we looked at overall activity while people were watching the videos, we see a sort of distributed pattern of brain activity. Obviously, there's lots in the visual cortex, but there's no difference when we compare the activity in our control group with our patient. So they're activating their brain in a similar way. When we look at activity during memory retrieval, there's also no different. Although if you look in the control groups, we see something that's very different from what we see in young people. We're not really seeing any consistent effects at all, apart from right back in visual cortex. So there's something slightly odd going on there. But then when we looked at functional connectivity, what we did here was we focused on one of these long timescale processing regions, the posterior cingulate cortex. We know that that's really important for representing information about in these videos. We've seen that before. And we looked for where in the brain was functionally connected with that particular region. And so we see a network of regions and healthy controls, both when they're watching and retrieving these videos. And if we look where there are differences with the patient, we see an area in the left hippocampus where there is less functional connectivity with this region compared to the control. So it's significantly reduced. Although as a caveat to that, we also know that this person's hippocampus on the left was shrunk as well. So to sort of see whether we've got any other information about whether that might be doing something functionally relevant, we look at that particular region where we found the difference between our patient. And then we looked at whether the functional connectivity in the controls actually correlates with the amount of details they can remember from the videos when we test them afterwards. And we do see a correlation. So there seems to be some evidence that this is functionally relevant, this connectivity between this cortical region and the hippocampus. Okay. Now, if we look at the patient from the Zhu et al. Study, which I should put on the slide, their ability to remember information even immediately after they'd learnt it. So if you're here 45 seconds of a story and immediately you have to report it afterwards, the patient is shown here as the orange dot. So they are pretty bad at doing this even immediately afterwards. And even for just single sentences, if it's a coherent sentence, they can do pretty well at repeating it back verbatim immediately after it's read out. But if it's an incoherent sentence, then they're not particularly good at this. So it shows that sort of even their kind of working memory for this type of information, if we classify it as working memory, is sort of borderline. It's not particularly good. Try and explain why that's relevant when I do this talk again. Okay, so now I'm going to look at the pattern of brain activity while they were listening to this narrative storyline. So here on the left, you can see areas of the brain where you see consistent patterns of activity while people are listening to that story. And so this is just within the controls, the young controls. I've got something coming up on my screen. I don't know if you can see that. And so you see very widespread effects, but they're centered on these long time scale regions that overlap with the brain's default mode network. Now, in the patients, can everyone see that orange square that's up there? Right.
Yeah, we can, yeah.
Do we know where that
is it Zoom?
Oh, well. I'm going to go away. I'll ignore it. Now, in the patients, you can see, so if we look at the similarity between this amnesic patient and the controls, the effects are not strong, but you can see significant effects in the same long time scale regions. And so these are showing that the patient's brain activity in these regions is significantly like that of the controls. So it's compared to just sort of randomized, you take the data and shuffle it up to create a kind of random distribution, then it's significantly more than that in these regions. But if we actually look at how similar that patient is, I've just highlighted in the posterior midline cortex, so this region here, the patient's similarity is very low compared with the rest of the controls. So although it's significantly above chance, it's quite a lot lower than we see in most of the control group. But these are young controls as well. So now, interestingly, I'm quite annoyed by this. I'm just going to stop share for a sec. Please move this window. Right. Okay, so this is showing parts of the brain.
There's still a big
you see
box over the slides.
What's that, sorry?
We've got like a big black box over the slides.
Oh, that's a shame. Okay, hang on, I'm just going to stop sharing. Reshare. It was working for me.
We basically can't see the slides at all.
Yeah, no, it's all right. I've come out of that. Let's start. There's a big reveal coming up, so I don't know.
The anticipation.
Any good?
Yes, it's perfect now.
Good. Okay. So the point of this one is to show the difference between the unscrambled, so the intact story and the scrambled story. Unscrambled. Okay, so it's unscrambled because they've reordered it so it all makes coherent sense. But basically, this is where you're seeing patterns of brain activity that are stronger when you're listening to the audio narrative in one continuous stream, so it makes sense to you, compared to when you're listening to it in a jumbled up order, so it doesn't make any sense to you. And what you see is more similarity in the patient. So this is kind of the key bit here, in posterior midline cortex and in the angular gyrus, when you're listening to the intact story. So this is pretty good evidence that this is accumulating and integrating the information in the story when it's coherent, and it doesn't do it if it's not coherent to you. And so you're seeing a difference here between the intact versus the unscrambled. And so that's what's being shown there. I'm not going to talk about this bit at the bottom, but going to go on to the last study. So remember, in this study, what you've got is 11 different short video clips that people watch again and again, and then recall again and again. And they're looking at whether on the pattern of brain activity, and first of all, they've just looked at a classifier based on whole brain pattern of activity. You can see, you can decode which of these things people are watching or recalling. And when we look here at the encodings while people are watching the videos, one looks like it's perfect in the patient. You get perfect classification on the pattern of brain activity from this individual. The weird thing is that there's also no actual difference between the patient and the controls when they're recalling these videos. So they're cued with the cue avalanche. They're told to remember it in as much detail as they can for a brief sort of 5 seconds or so. And the activity during that period seems to be no different from the controls. But then if you look at your ability to take brain activity during encoding a specific video and then try and classify which one you're recalling, then in that, it's doing much worse with the patient compared to the controls. So it doesn't seem that the patient is reinstating the pattern of brain activity that's elicited at encoding when they're remembering it later, to the degree that they are in the controls. So that's the main sort of take-home finding. They look at this also in different regions of the brain, and effectively what you're seeing up here is that in many regions of the brain, you can do this classification. They're sort of coded by heat map according to how well you can do it. You can do it during recall in many regions of the brain, both in the controls and in this patient. And actually, even in the cross condition, you're able to do it in quite a few regions within this within the patient NC. And this is showing over here that actually the classification is better in the patient during the encoding sessions than it is compared to the controls. And in the retrieval, it's sort of half and half in the recall phase. And this cross classification, there's only actually activity in one network, which is significantly poorer in this patient. So there's not a lot of evidence for much going on that's different here. So I want to sum up, going back to the questions that I asked at the start. So is the processing of ongoing events in these long timescale cortical regions normal? Well, we certainly haven't got any strong evidence that there are differences or it's impaired, and that's consistent in all studies. But that's possibly down to a lack of sensitivity. Probably the intact versus scrambled pattern similarity result reported by Zhu et al. Is the best evidence that there is kind of normal processing going on in these regions while you're listening to a kind of continuous event unfolding. And this patient showed close to the lowest amount of similarity, and also they weren't using age-matched adults to compare the patient to. So it's not clear what the results would have looked like if they had. Are hippocampal responses related to memory encoding abnormal? This wasn't really assessed in any of these studies, and it's obviously, it's difficult if you've got damage to a region to then look at responses in that region. Are the interactions between these long timescale regions in the hippocampus abnormal? So we looked at functional connectivity and found that yes, the functional connectivity was abnormal between posterior cingulate and the hippocampus, but there's an issue here that the tissue in that region is probably compromised as well. And are processes during retrieval abnormal? So there is some evidence from the St. Laurent study that that was the case, but actually during the retrieval trials themselves, classification was normal. And I mean, in our study, we just found that older participants seem to activate their brain less during retrieval, and so it's hard to see these effects. So to sort of sum up all of that, from these studies, we've got some tentative support for these current theories of how event processing and memory work. But you also, when you run these type of studies, find results that are surprising and maybe counterintuitive. And so actually, or the result of doing studies like this, I think highlights the fact that we really need to find out exactly what's driving these fMRI effects in healthy adults. So why it is that you can have someone with memory problems that can apparently activate their brain normally during retrieval. And establishing what kind of variability you get in these fMRI effects in young and old adults, because if there's very variable results, then you're not going to be able to see much in patients either. So it's not the problem with the patient studies, it's the fact that we perhaps don't understand, we're basing our theories on effects that we haven't understood particularly well, based on fMRI studies in young people. And that's sort of the depressing conclusion that I'll be trying to end up with, but in a positive and illuminating way. And anyway, wanting to thank Chrissy and James, who have left my lab now, but who did this research, and the ERC for funding it. Sorry for overrunning a bit. The end.
Thank you very much, Chris. Does anybody have
1 minute?
Eleanna?
Hi. That's probably quite obvious. It looks like it should be quite obvious for me to understand, but I don't think I got it properly. See the results in the intact and scrambled story. Could you kind of like go over them for me again? Kind of like...
I can do. It's possibly not something that everyone in the meeting needs to hear. So
yeah, of course,
I mean,
not all of them, but like the main.
If you're very interested, I can go over it. But
the main conclusion, basically, were they different in how they process the story, or were they the same? And
I mean, I do have this talk recorded, so you can rewatch that section.
Yeah, sure, of course, yeah.
There was no difference between the
okay.
patient.
Okay. Yeah, thank you.
Cool.
Paul, yeah.
Chris, it might just have been me, but I wasn't clear towards the end when you were looking at brain activity in encoding and in recall and in cross condition. I wasn't clear what cross condition was. What is that?
So you're recording brain activity while people watch and remember the same events many, many times. And the idea is that you can take the activity. So if one of the videos is Bugs Bunny, I can take the brain activity while someone's watching Bugs Bunny, and I can use that pattern of brain activity to then try and classify which of the retrieval trials is Bugs Bunny. And you can do that successfully in the healthy adults, and you can do that less successfully in the patient.
Yeah, so you're coming up with a classifier to use during recall.
Yeah.
So what's the cross one?
So you're basing if it's just based on retrieval, then you're taking your pattern from one of the retrieval runs, and you're taking your classifier from 6 of the runs, and you're trying to classify the retrieval trials in the 7th run. Whereas if you're doing it the cross one, you're taking it from the encoding trials and classifying the retrieval trials.
Okay, right, yeah, I got it. Right. Yeah, I wasn't there. Right, right.
Ed, do you have a question?
Yes, nice talk, Chris. So
it really wasn't.
More in terms of, sorry?
It really wasn't, but it will get better.
No, it is. I enjoyed it very much. So one thing that I was kind of expecting something based on what you said earlier in the talk, but it didn't really happen. So basically, you were talking in the beginning about event boundaries, and that was seemed to be an important part of the background. But then I didn't see anything in the designs that were looking specifically at event boundaries, like there was no switch between scenes. So I'm just wondering whether maybe I don't know if you can frame it differently in terms, not event boundaries, but something more general about memory for scenes, unless you are going to talk more specifically about event boundaries. But it could be just this is not my area, so I'm not seeing the link there between event boundaries and the paradigms. But yeah, the other question I have is more about stats. So I'm not very familiar with these sort of patient studies where you have a single patient and you can compare. You're looking at significant differences between one patient and then a group of controls. And so I'm just wondering about your conclusion at the end, where a limitation is that it's quite noisy in young healthy controls. But I'm wondering whether also part of the reason why the picture is not clear in the studies you talked about is because that that patient might not be very representative of amnesics in general.
Yeah, I mean, I think the point is that the effect sizes in the reason why you can do single case neuropsychological studies, right, is because the effect sizes in behavior are massive. They're off the scale, and so you can get someone who is so out of the range of normal people that they're clearly impaired, and you can see that in sort of parametric and non-parametric stats. You can do the same stats on fMRI data, and you can see whether or not people are significantly impaired using our ways of saying what's significant or not. And I guess the point is really that even though in terms of someone's memory performance, they are off the scale impaired, if you look at their brain activity, it's not so different from the controls. But it might be that because the variability in the controls is such that you can't really get it. So unless you're talking about sort of super reliable effects like activating FFA in groups which you see pretty consistently, then you just might not be able to see whether someone is activating the brain normally or not. And we need to establish how reliable our effects are. But which is obvious, but it's still the case that a lot of theories and data are discussed like, well, we've got these, highly significant effects in a group of young people, therefore we know what's going on. Whereas actually these effects certainly aren't reliable to be able to then see whether at the individual level, someone, despite the fact that they are grossly amnesic, We still can't see whether actually their pattern of brain activity is unusual. And I think that's kind of the point I'm trying to get across.
Thanks.
Thank you very much. I think we should probably stop there, but if anyone wants to chat, I'm happy to leave the Zoom link open.
I can stay on for Claire if you had a question that you wanted me to answer. Everyone else can go.
I did, but I don't know if it was a stupid question, so I lowered my hand.
Well, quite a few people have left. You could still ask it.
I guess I was just like returning to your conclusion about how even in kind of healthy populations, we don't quite understand the connection between brain activity and the kind of quality of long-term memory. And I couldn't remember exactly which method the 3 papers used to assess memory. But I was wondering if we needed to be kind of more clever in how we kind of tease apart the kind of representations people have of events in order to kind of strengthen what we can say about that kind of correlation.
Well, so like in the last study with the classification of the very, very short events. So, I mean, they tested memory in a rigorous way that you would do. They got the person to describe in as much detail as they could. They went down and they sort of marked off the level of detail in the responses and stuff. And you get a very fine-grained measure of how accurate his memory was. Yet, the fact that you could decode in the recall data what it was he was looking at suggests that actually in that fMRI data, they're looking at sort of cue-evoked activity or something super generic about, like, currently I'm thinking about avalanche. I'm not actually remembering the specific avalanche video that I saw 6 times before, but that's sufficient to put a pattern of brain activity in wide areas of cortex that is specific enough to decode it to that video and not any of the 10 other ones. And so I think that's kind of what I mean. It's like, you know, we'd like to think we're looking at sort of super detailed recall, and actually it's really helpful to stick people in the scanner who've got really bad memory, because if you still see the effects, then you know that your task is not actually doing what you think it might be doing. So it's inconvenient to run these studies, but it can actually tell us quite a lot about what's going on. That's sort of what I meant.
Thanks.
Hao-Ting, were you gonna try and coach me?
Yes, so can you just show me the slide again?
Yes, I can. Feel free to leave the meeting.
No, and this doesn't need to be recorded unless you want it to be recorded, and he can practice multiple times.
Yeah.
Recording going.
Stop! Don't record it. So.
Okay.
Sorry, let me just share the screen again.
Do you want me to stop the recording?
Yes.
Hang on. Where is it?